Hello everyone, welcome back to Algebra 1 with Miss Betsy. We are continuing our work with equations in Chapter 4 today. If you are using the text that I am, this is what your book looks like. It is the second edition of Pre-Algebra for Christian Schools and it's published by Bob Jones University Press. Edition 3 is not directly compatible. They've changed the order of the topics around. We're going to be on page 143 and we're just doing some more work with equations today. So let's go ahead and pray. I've got a lame joke for you and then we'll get started. God, thank you again for who you are, for your love for us, and for giving us the ability to think and to reason and to learn new material. Lord, I ask that you would help us to study, to show ourselves approved to you, and that you would give us the ability to comprehend this material today. And I thank you that you love us, and I pray in the name of your Son, Jesus, amen. Okay, this one, you have to think about this for a little bit perhaps. What do you call a crying camel? I've never heard this one before. What do you call a crying camel? Well, a crying camel is a humpback whale. You know, humpback whale. So, I thought that one was quite an interesting use there. You have all sorts of whales in the ocean, then you have a crying camel who is a humpback whale that goes across the desert. So, if you are familiar at all with construction, or if you looked at houses or decks or porches that are just leaning every which way and they're not solid or they're caving in on one another, you know that either that foundation was not good to begin with or the foundation has failed. And just as we who believe in Jesus know that Jesus is that solid rock of the foundation on which our life and our faith is built, so also in algebra is the fact that equations are the foundation on which all of the rest of algebra 2, all of the math and science out there that has algebra as its basis, those equations are the foundation on which the rest of your mathematical involvement in life and in school is going to be built. And it's really, really important that you get a good solid foundation in equations. So we're going to be doing lots of practice with those. You will always be working with equations in algebra, and the better you get at solving equations, the more readily that you are able to troubleshoot your own problems, the quicker you'll gain a good level of comfort and expertise in algebra. So let's look at example 1 on page 143. This says solve 3x plus 2 plus 5x minus 7 is equal to 28. This is example 1 and it says solve. And we know that you can only solve something where you have a verb involved, and it's usually an equal sign. Sometimes later on we'll solve inequalities. You can come up with a solution if something is greater than, less than, greater than, or equal to. But typically you're going to solve an equation that involves an equal sign. And this is a long string of letters here, a long string of math here. And I can already see that we have some like terms that we want to combine first. 3x, of course, and 5x are like terms. 3 plus 5 is 8, so we have 8x. And then our constant terms here of a positive 2 and a negative 7. Those are like terms also, and we combine those. 2 minus 7 gives us a negative 5 is equal to 28. So this is not much different than what you did in section 4.3. You have an algebraic equation, you combine like terms. Now you inspect this equation to see what has been done to the variable. Two things have happened. First, x was multiplied by 8, and then 5 was subtracted from that product. So in order to solve for x, or to isolate the variable, we're going to apply inverse operations to what happened to this variable here. First it was multiplied, then it was subtracted, but we're going to do it in reverse order. So we want to undo the subtraction of 5 by adding 5 to both sides of the equation, and you now have 8x minus 5 plus 5 is equal to 28 plus 5. Plus 5 minus 5, of course, goes to 0. We have 8x is equal to 33. And let me make sure that they're giving us one that's unequal, and they are. Is not an even number. Now we simply have 8 times x. So there's only been one operation performed on the variable x, which is multiplication. The inverse of multiplication is division. So we are going to divide both sides of that equation by 8. We see that we have a common factor of 8. Of course it cancels, because this is what we're trying to do. We're trying to find out what 1x is equal to. X then is equal to 33 over 8. There are no common factors, and we are not going to transform or translate this improper fraction into a mixed number, because as long as we have a rational expression reduced to lowest terms or expressed in lowest terms, then we're happy. Now could we go ahead and check this? Sure. We can go ahead and substitute back into the original equation. But this is all that is being involved here. I'm going to let you go ahead and look at the bottom of page 143, because that's where they've gone through the check. They substitute 33/8 in these two separate places, and then do all of the arithmetic that's involved to verify that 28 is in fact equal to 28. So now let's go ahead and move on to example number 2. This one we're going to have to distribute. So the problem is it's involving a few more steps. These are things that you have seen before, but you just haven't done them all in one problem. We want to solve 4 times the quantity x plus 5 minus 3x is equal to 24. So before we can isolate the variable, we need to collect like terms. But before we can even do that, we have this multiplication here that we have to perform first. You cannot combine x plus 5 within the parentheses, can you? So you use the distributive property. 4 times x is 4x, plus 4 times 5 is 20. This is not 4x plus 5, it's 4 times x is 4x, plus 4 times 5 is 20, minus 3x is equal to 24. And you need to be careful to show your steps written out like this. Now we can combine like terms. 4x minus 3x is x, plus 20 is equal to 24. Now we can go ahead and isolate the variable. What has happened to x? It's had 20 added to it. What is the inverse of addition? It is, of course, subtraction. So we are going to subtract 20 from both sides of that equation. And if you forget to do the subtraction on both sides, your equation's out of balance, but you don't realize it. You solve it anyway, and that's why you end up with the wrong answer. Now you have x is equal to 4. How would you check that? You would substitute back into the original equation. And you would have 4 times 4 plus 9 minus 3 times 4. Is that equal to 24? Here, we can combine within the parentheses. 4 times 13 minus 12. Is that equal to? Whoa. 24? 4 times 13 is 50. Okay, what did I do wrong? Oh, 4 plus 5 is 9. I said 4 plus 9. Helps if you substitute correctly, doesn't it? 4 plus 5, because I was moving on to the next step. 9. 36 minus 12, is that equal to 24 now? Yes, now that I've figured out where my mistake was, I have verified that our solution that we arrived at of x is equal to 4 is true. Okay? Now, let's go ahead and look at example 3, which, lo and behold, is a word problem. You weren't expecting that, were you? But we can still do it, because you've gotten some good practice in section 4.2. This says, John's mother is 4 times as old as John, and John's brother is twice as old as John. If you find the sum of their ages and add 3, you get 80. What is the age of all 3 people? So we're going to have 3 answers, but just 1 variable. So let's look at the problem and see what we want our x to be equal to. It says John's mom is 4 times as old as John. John's brother is twice as old as John. Mom's age and brother's age are being expressed in relationship to John. So we're going to say, let x be John's age. So how old did we say Mom was? Mom was 4 times as old as John. However old John is, Mom is 4 times more. So 4x is Mom's age. And how old is brother? Well, brother, I think, was 2 times as old, wasn't he? John's brother is twice as old as John. So John is the baby here. Twice as old, so this is brother's age. Now we have identified our variable of x, and we said that's going to be John's age. And we expressed these 2 other word phrases, 4 times as old as John, 2 times as old as John, using the variable. Now we have to decide, how are we going to make our balanced seesaw? What are we going to put in those boxes? Well, this says if you find the sum of their ages and add 3, you get 80. So the sum of their ages, x plus 4x plus 2x, sum, of course, is what you get when you add a group of numbers together. The sum of their ages plus 3, you get 80. So that is the equation that we came up with to solve this problem. All right? Now we can collect like terms, can't we? 1, 4 is 5, and 2 is 7. Do not forget that you actually have 1x over here. The coefficient you don't see, but you usually don't say, Mom, I would like 1 apple. It's, Mom, can I have an apple? You know, if you want 2 apples, you say, Mom, I want 2 apples. Otherwise, you just say, Mom, could I have an apple? That's 1x. Plus 4x is 5x. Plus 2x is 7x. What has happened to the variable here? X was multiplied by 7, and then 3 was added to that. We're going to undo this by applying inverse operations in reverse order. First multiplication, second addition. So we're going to undo this addition. What is the inverse of addition? Well, of course it's subtraction, and I'm not going to use a different color, but I am going to make certain that I subtract 3 from both sides of the equation. What you do to one side of the equation, you must do to the other side of the equation. You now have 7x is equal to 77, and I was going to write the answer again. We multiplied x by 7. Now we are going to divide x by 7, and we have x is equal to 11, which is John's age. Brother's age is equal to 22, so you have to put John and brother, and you have to have mom, who is 44. Because it said, what is everyone's age right now? 44 plus 11 is 55, plus 22 is 77, plus 3 is how we got to 80. So that is how you would solve that problem. Several steps involved there, but still nothing that you're not perfectly capable of handling. Now, these last two examples that I'm going to do here are a little bit weird, and you really don't have a whole lot of occasion to use them, but you need to know how to do it because it might show up on a test or it might show up as a bonus problem. So make sure you pay attention to these. Your book says at the bottom of page 144, you may be surprised that it is necessary to solve equations to convert repeating decimals to fractions. Well, if I ask you to convert this decimal to a fraction, I don't want to do, let me see. You want to convert 35 hundredths to a fraction. Well, 0.35, that of course I just pronounced it, 35 hundredths. Is that reduced to lowest terms? No, it's not, because there's a factor of 5 in common. This is 5 times 7, 5 times 20. So you cancel out the common factor of 5, or you divide both the numerator and the denominator by 5, and you have converted the decimal number, 35 hundredths, to its fractional equivalent, which is 7/20. But how in the world are you going to do something that looks like this? 7.333, which is 7.3 repeating. How in the world could you possibly convert this nonsense into a rational expression? Well, there's a technique that you use, and I'm going to show you, I'm going to step you through example 4 and example 5, and this is what we have. Example 4 says, convert 2.3 to fraction form. So you have 2.3 repeating to fraction form. This is the methodology that you use. First, you assign the variable x or whatever to be the repeating decimal that is given to you. Now, you're going to, right here, you want to multiply both sides of this equation by 10 to move one repeated pattern to the left of the decimal. See, what we're going to do is allow the repeated parts to cancel out. We have one decimal of repeating here, only one decimal repeats, so we're going to multiply by, what is that? That's in the tenths. So we're going to multiply by 10. We're going to have 10x is equal to 23.3 repeating. Remember, when you multiply by 10, you're going to move the decimal point 1 unit to the right, one place to the right. If we were multiplying by 100, we would move that decimal point 2 places to the right. Now, it doesn't matter because those 3's are just going on forever. We just want to move the location of that decimal point. Now, we have a value for 10x, and we have a value for x, and we're going to do something really weird. We're going to subtract them. We are going to say that 10x is 23.3 repeating, and we're going to say that x is 2.3 repeating. And we're just going to line them up this way. Come on. X is equal to 2.3 repeating. And what this lets us do is it lets us subtract equal amounts from both sides of the equation. 10x minus x is 9x. 23.3 repeating minus 2.3 repeating. All of that repeating stuff drops off. And you have 21.0, or you have 9x is equal to 21. And now you have this equation in a form that you recognize. X has been multiplied by 9. The inverse is to divide by 9. And we have x is equal to 21 over 9. So what you have done is you have converted a repeating decimal to this fractional form, which is 21 over 9, and I'm getting tired of doing videos. This is not reduced to lowest terms, is it? No, because that's 3 times 7, 3 times 9. So the reduced form of this fraction is 7/3. And what this exercise illustrates to us that even repeating decimals are rational numbers because you can express them as a fraction. It's a weird way to do things. Let's look at this next one. Convert 7.292929 to fractional form. Okay, what are we going to do here? Well, first here we're going to see what is repeating. We have 2 digits that are repeating. So with our repeater bar, we have 7.29 that repeats. So that's what x is going to be equal to. X is equal to 7.29 repeating. Now we want to be able to move our decimal point 2 places because there are two places here that it repeats. So in order to move our decimal point 1 space to the right, that's times 10. Another space to the right is times 10. So we're going to say 100x becomes 729.29 repeating. Do you see what we did? We wanted to multiply by 10, 100, 1,000, whatever, so that we have our repeating part only to the right of the decimal point. Because this is 7.29292929. This is 729.2929. Then we set up the same type of problem. And we say that 100x is equal to 729.29 repeating. And we're going to subtract from that the equal quantities. Because remember, you can subtract the same thing from both sides of the equation. That's all we're doing here. It's just that these don't look equal, but we said they are equal. We say x is this. So we're going to subtract 1x from the left side, and we're going to subtract 7.29 from the right side, and we have 99x is equal to 722, period. Because our repeated pattern of 0.29292929, every bit of that is going to subtract out. What do we do now? We divide both sides of this equation by 99, and we have that x is equal to 722 and 99 hundredths. 722 over 99. I don't think that reduces. This cannot be reduced. So once again, we have demonstrated that the repeating decimal 7.29 repeating is a rational number because you can write it as a fraction this way. What I'm going to do with those weird examples there, example 4 and example 5, is I will have a bonus on the test for chapter 4 that is a repeating decimal. If you have taken the time to watch this video, you will know ahead of time. Matter of fact, I'm going to tell you exactly which one it's going to be. Example 4 is going to be the bonus for section 4. I'm sorry, for the chapter 4 test. It's worth 5 points. Make sure that you can duplicate it for me, and also try and understand what they're going on here, but you're not going to use it a lot. It's just a little technique that they want you to know. Once again, if you have questions, send me a text, do your best, or I will see you in class on Friday.